Hello, this is the next video in a playlist that I'm calling Hypothesis Testing, and here we're in part 6 of a little mini-series within that playlist. We're looking at two-sided uniformly most powerful tests in the one-parameter exponential family. Now, a must-watch is part 1, where we talk about the theorem that we're going to use to prove that this two-sided test is uniformly most powerful. It's really just an extension of the Neyman-Pearson limit. And then in part 5, we specifically talk about the binomial setting, and then this is the R program follow-up to that binomial setting. So here let me remove the objects from the list. Here we're looking at, is the binomial parameter less than some value P1, or is it greater than or equal to some value P2, or is it between those two values? And I'm randomly picking 0.45 and 0.75. We'll change those in a minute or two. We're going to let alpha be 0.05, n equal 25. Now, in CR, it stands for critical region, we're going to create a matrix of all possible combinations of C1 and C2, and then we're only going to keep the values where C1 is strictly less than C2, because that's a requirement of the hypothesis. And then we're going to create these these probabilities, P1 through P6, and I'd refer you to the video on that, part 5. And then we're creating gamma and gamma 2, gamma 1 and gamma 2, which make these side conditions equal to alpha. But in the video, part 5, we noted that gamma 1 and gamma 2 can only be between 0 and 1, so we're only going to keep those possible values. And then we're going to see if this side condition does equal alpha. So it should be, I created alpha 1 and alpha 2, and they both should be 0.05. And if you look down in the lower right corner, both of those are 0.05. So our critical region is 15 and 16. So let's create the power curve for this setting and look at that. And this is it. So this is the power curve for different possible values of the true probability of success. Now, our null hypothesis was that P is less than 0.45, or is it greater than 0.75? And notice that the power curve is strictly less than 0.05, and at those values, or at those critical points, it does equal 0.05, and the power increases in the alternative region with a maximum of about 15% power. So now let's do a computer simulation of those, and let's first look at the boundary points, 0.45. And so let's do 500,000 replications. So I'm creating a matrix that holds all these values. The number of rows is 500,000. Number of columns is n, which is 25. So it's a 500,000 by 25 matrix. So each row represents a sample of size 25. Then we create the row sums, and then we check to see if it's in the rejection region or not. And then we reject with certain probabilities. And then we tally them up, the trues and the false, and notice that it's 0.4999, which is roughly 0.05, as it should be. Let's do 0.75, and this should also be 0.05, and it's really close. And I'm going to peek at the graph because I already forgot. So at 0.6, it should be a little over 15%. So let's put 0.6 here. And then calculate power. And it's, just a little over 16%. Now, to show you the versatility of this program, let's change the parameters. So let's assume that we're testing the null hypothesis, that is the true P less than or equal to 0.55, or is it greater than 0.65? And let's change our sample size to 55. Those are, I got to run those. And now let's recalculate, or find in the critical points, C1 and C2. And So that's all of this. I'll just run it, and boom, it went through every possible C1, C2 combination. It found the only unique solution, and this is it. So the critical region is a C1 of 33 and a C2 of 34. And let's look at the power curve associated with this. And it's this. Notice at the boundary points, 0.05 and 0.65, it's alpha, it's alpha 0.05. And the power, sample of 55 is not very big for that tight a difference that we want to detect. So let's jack up the sample size. Let's make it 155 and recalculate the critical region. And that's it, 92 and 93, though that's the C1 and C2. The boundary is met, so now let's look at the power curve. And here, well, it went from not much to a little bit more. So that's such a tight difference that we want to detect. And we're in the middle where the variance associated with the binomial parameter is the largest. If we went a point, 0.1 difference on the tail, the power would be way up. And actually, let's try that for fun here. So let's make this 9.5 and 8.5. So it's the same 10% difference, same sample size, but now, and we'll just go all the way through the power curve, and notice it went up quite a bit. And that's because the variance in the tails are much smaller than in the middle. All right, well, that's it. This is the program to calculate the uniformly most powerful test, two-sided test, in the binomial setting. So hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.